where we left off last time was around the fitness. Now, I showed you here there is a mean squared error fitness, but if we scroll up to here, where was it? No. Mean squared error. I've got two versions of this function. Mean squared error fitness, all it really does is wrap the mean squared error function. And the reason for that is mean squared error is a fairly general function you might want to write. This is a function. This is the independent variables, dependent variables. For each of those, apply the function to it, calculate the difference squared, add it all up, divide it, mean squared error. It's a general purpose function, and it is easy to test, which is a good thing, right? So that's great. But deep, in order to use deep, there's a couple of extra things we got to do here. Sure, there's some exception tests here, but first and foremost, a candidate solution within deep with genetic programming is the S expression tree. It's a tree. It's not a function that can be called, but it's a tree that can be turned into a function. And that's what this does here, toolbox.compile. This is a deep thing. I give it the individual, this is the tree, and it also takes the toolbox. I'll show you, I'll go back up in a moment so we don't forget what we saw last time, which was Friday, right? Yeah. We compile it, so this is now a callable function, the candidate solution as a callable function. We give that to mean squared error, get the result, and then we return the value. But in deep, because deep is designed to work with an arbitrary number of objectives, here when we're doing symbolic regression, typically we only want, usually we're minimizing the mean squared error. There's a single objective. Sometimes people will add a second objective to minimize the tree size, but that's not important right now. But deep is designed to work with an arbitrary number, so you're supposed to return a tuple where the size of the tuple is the number of objectives that you have. Well, here it's a tuple, but there's only one value in it. So the wrapper function does some error checking, does some exception checking. It compiles the individual to a function that can actually be run. It then calls the actual mean squared error function, gets the result back, and returns the result as a one-dimensional tuple. Okay? And this is just to make deep happy. If you're thinking to yourself, why not why write that as a separate function? Why not throw this just inside the other function? And you're right, I could have done that, but I like it better this way because this is a more general purpose function that I think is a little easier to test on its own. So it makes sense to pull it out, in my opinion. When we go to here, the mean squared error fitness, when we're setting up our deep, when we're setting up the toolbox, we are registering the evaluate function. We're registering something called evaluate. Its function is mean squared error fitness. And then this right here is assigning the arguments, the keyword arguments here for this function. Toolbox, independent variables, dependent variables. Toolbox, independent variables, dependent variables. So whenever we call the actual evaluate function, it's going to call this function, and we need to pass it the one outstanding argument, which is, well, what's the individual being compiled? Again, this is all how to work with deep. If you don't like the way deep is designed, take it up with deep. Leave me alone. All right? Then bloat control. Remember we talked about bloat, how bloat is an issue? Well, there's a couple of things people will do to help mitigate bloat. One that I already kind of just mentioned was you actually make the problem multi-objective, where you make one of the objectives tree size, and you minimize mean squared error, and you also try to minimize the size at the same time. People will do that, and it actually works pretty well. Deep provides a relatively simple way to control for bloat. Basically, it's saying on your crossover and mutate, you've got some restrictions on how big the trees can get. That's all. So when you're doing crossover and mutate, don't let the height get too big and don't let the number of nodes get too big. Those are separate variables, even though they're obviously connected. Separate values, pardon me, even though they're obviously connected. But that's what the decorate here is for. There's a lot more stuff you can decorate your GP with. This is just the simple bloat ones that are good to have. And then bookkeeping. Deep actually provides a nice handy way for keeping track of like what happened throughout evolution. There's something called the Hall of Fame. It'll keep track of like your best chromosome each thing. We can create like some statistics here. We can create a fitness statistic, which is based off of the individual's fitness values. We can take a size statistic. How big is the tree? It's going to be like the length of the tree. That's the function we're going to apply to the individual. Obviously, statistics takes a function. This is just a lambda expression to get the fitness from each individual. This will get the length of each individual. Another stat, get the height. And then because we have multiple statistics, we can say, okay, well, I want these statistics I want to keep track of, and I'm going to register. I'm showing you a lot of here's how you do it, but I think once you see an example of what it produces, it'll make a lot more sense. And then I want the mean, standard deviation, min, and max of each of these things. I'm going to go back up in one moment. This is an example of the output we see this is an example of the output we see based on the statistics. The fitness section, we got average, okay, max, generation number, max, min, and evals. The table kind of got all messed up because of tabs. Standard deviation. The same for the height, same for the size. So it generates this like table. Here, I added this. You'll have a row for each generation. So it tells you each generation's the average fitness of the population, the worst fitness, the max, the min fitness, not that bad. I don't know what n eval is off the top. Standard deviation, the height of the tree, average 2.3, max is 4, min is 1. Some of those trees were getting pretty big. And size as well. Whoop. Yeah.
I think n evals is the number of times that to evaluate the fitness. It's a bit smart in that it only evaluates fitness of something that was like mutated or crossed over.
Is that right? Yeah. Nice.
But the flag if it needs to reevaluate the fitness essentially.
Nice. So then, when running it, going back up, all we have to do is say, okay, create a population. Well, based on the population that we registered all up here, all of this stuff right here. Register, 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 population, which ended up based on the individual, which ends up being based on the generation tree. Create a population. Whoop. And then use the simple EA simple. There's a lot of options available in the deep documentation if you have a look. Population toolbox, crossover, mutation, generations. I set the statistics, Hall of Fame, and I set verbose to true because I want some output. And that's basically it. And then when I'm done, I print out the Hall of Fame. Here I'm printing out the Hall of Fame at index 0. This will be like the latest one. And then it's fitness. You'll notice, if you go through the deep documentation, did anyone here get deep to print those trees out, like generate those plots of those trees, those pictures? Yeah. Did you get it figured out? No. So once upon a time, I got it figured out. And then a year later, I figured it out again. And then since then, I haven't refigured it out. I forgot how I did it. And I'm not going back to try to figure it out because I remember it just being a nightmare, pain in the ass. If you figure it out, write it down, what you did, and let me know. Because, yeah, it's like, oh, it's simple, just do this. And it's like, well, that has a lot of dependencies, which has dependencies, and do you have the right version of this, that, and the other? It's a whole thing. So it's a bit of a nightmare. If you want to print out a candidate solution, you can just print out the chromosome, but you have to convert it to a string first. So Hall of Fame at index 0 is a chromosome. When I convert it to a string and then print it out, it'll be like something that looks like this, which is 1 plus x negated, which is just like, okay, it's x plus 1 is how I would write it, right? Because the two negations cancel each other out. And okay, arg0 would be the first argument. Call it x, typical. And this is its fitness value, 0.009. Not bad, right? So there. Y equals x plus 1, and its fitness is roughly that. Any questions about that? Yeah, because it's a tuple. It's a tuple with one value in it, so that's what you see. Because there's only one, it's only single objective, and so the fitness is a tuple of the number of objectives, and there's only one, so you see that one. Now, one thing about genetic programming, not just for symbolic regression, but for genetic programming, is it will produce some funny results that might require some simplifying, right? All of these are equivalent. They are equivalent expressions, but it's kind of silly, right? Like, okay, x minus like here. For fun, let's just talk about some of these. If I can find a marker that works. Does this one work? Hey, not bad. So we're saying arg0 is just x. So we've got x minus the protected divide of x divided by negative x. Well, that's just 1, or negative 1, and then negative 1, negative 1, that's positive. Oh, that's just x plus 1. Right? The next one. What is happening? We are adding, okay. Now let's just go to the last one, because that one looks the craziest. So we are saying, okay, we are saying x divided by x, x divided by x, multiplied by x divided by x, and we are adding that to, whoop,
X divided by 1.
yeah, plus, so yeah, x divided by 1 multiplied by x divided by x. Really sophisticated look at expression, right? Like, wow, our GP system is so smart. But of course, that's just x plus 1, right? Any questions about that? So if you're wondering, how do you get GP not to do that? You don't. You just go in and you go like, all right, well, what the hell does this actually mean? Pardon? If x is 0, then y at that data point would be, well, no, would still, like actually that's a good question. Like if it's actually being evaluated and arg0 is 0,
Protected divided
makes
makes infinity.
it infinity.
Presumably x equals 0 was just not like in the set of test points, so it never had to hit that.
Ah, yes, that's a good point. There was no actual x equals 0. That's a good point.
Because the squared error would be infinite.
Well, so that particular example, yeah, that's a good observation. So with this particular one, protected divide was actually not necessary because none of the data points were 0 that the data was fit to, right? It was always like 0.000000001 or something. So that's a good point. But for us, we can look at this and be like, well, that's 1, that's just 1, right? Plus, that's x times 1, that's x. Oh, that's just 1 plus x. Yeah, right? So it's still a value, it still is equivalent if you simplify, except for the fact that we're cheating a little bit with the divided, like with this.
We don't really know like if we're legally allowed to do that simplification or not. We can like kind of hope that we were allowed to, but
Well, as far as how this system was defined, as far as GP was concerned, in its universe that it was existing and running happily, this is equivalent to 1. Because it never got a chance to do. This is true for every value except 0, but it didn't matter because it never had a chance to.
0 wasn't like actually in the domain.
Exactly, so it didn't care. Now, if we generalize, we'd have a problem, except we can simplify this before we get to the place where 0 is actually in the domain.
Is there, like, knowing that this exists in deep, did they make any simplification?
Oh, no. But you have to understand, this is a peculiar case of, now, if 0 was in the domain, situations like this would die out, right? Because its fitness would skyrocket if on the 0 case. Sorry, its fitness would become very bad, right? Oop. But the key point here is the data, just like you said, it fit data where where 0 was not in the domain. Thus, when we do the simplification on everything that's in the domain, it's fine. Then if we generalize this to real numbers in real life where 0 is in the domain, it's already simplified out. So it's irrelevant. So everything is okay in the end. Let's not focus too much on basic arithmetic. Any last questions before we jump to me working through an example? All right. We can get rid of this. So now to go through an example with deep. Who here's got deep running? Okay. You already submitted it? Nice. All right. So, so yeah, a total of 20 instances are made available on the GitHub repo. All instances are made of tabular data, blah, 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 blah. The language that I gave you here, GP. Here. First, let's go talk about this code a little bit. So here's some hyperparameters. Here I've just got some constant set for where you can go find, like I've hard-coded the relative path and then the specific data file I want to fit. My protected divide, my mean squared error, my mean squared error fitness. This is all identical to what we saw on the notes on the website. And then we have this. Load the data, set the language, set what the fitness is, how to generate a population, what evaluate is, selection, mutation, some bloat control, bookkeeping setup, and then there's the run, which it looks like a lot of lines of code, but really it's only 2 function calls. Create the population, and run the algorithm ZA simple. And then in the end, it returns the final population and a log. And then when we're done, we can print out some results. So let's have at it. Is it going to work, or is it just going to be thinking nothing is available? And I don't, what is VCS? Version control? Why is it? All right, well, PyCharm is becoming aware of itself. Let's go back here. The language that is included in the provided code may not be sufficient to effectively model the data. So for those of you that worked on assignment 2, and we're trying to fit various pieces of data. Oh, did you do a typed problem? You didn't? So, all right. Did you end up having to modify the language for some of those data sets? A little bit. So, a strategy for managing, oh, I already said this. A strategy for adding bloat is to add negative selection pressure to larger chromosomes, right? Oh, is that? We could skip this. This is me saying, go run it and play around with it, which presumably everyone in here who's started the assignment has already done. And then I was saying, as an activity, go and add to the fitness function the size of the tree to try to minimize that. And let's see if we could do that together, actually, just simply. Is there, I don't know, I can't even run it yet. It's still, stop. I can't even stop whatever this is. Oh. Where was the runtime warning? Invalid, encounter, and subtract. Probably because in one of the fitness evaluations it was trying to do something that raised a runtime warning. As any array minus array mean. I'm guessing like maybe this was trying to run when the array was empty or something. I'm not 100% sure what the specific warning is about, but I'm not too worried about it. So here's some results. And in the end, it looks like it actually never got to, oh, here we go. So what do we have here? Protect to divide thing by thing. Okay, so 1. Hold on. X minus 0 minus 1 minus x. So x minus, so we have negative 1. 0 minus negative 1. We must have messed, oh no, then we must be skipping a step here.
Then we get x.
Well, no, if we took out the x, whatever, we're trying to simplify in our heads when we should be doing it on paper. Either way, I'm willing to bet this evaluates to x plus 1, right? Assuming I was using the same data set. Okay, here, let's actually simplify it. Just to make sure we're not crazy before we carry on. All right, let's see. So we have, here, let's just kind of do it like this. And then this is just 1, right? Notwithstanding what we've already talked about. And then, oh, I'm messing something up here. Whatever, okay, so here we have x minus 0, right? So this is x minus 0, which is just x. And then so that's x minus 1. And then we minus x. And then we have x minus 1 minus x. So that's negative x minus 1, right? And then we do 0 minus that, and then we negate it. I'm trying to do it too fast on the fly. I'm messing up, but either way, I'm pretty confident it evaluates to x plus 1. If I'm wrong, let me know in the comments below. All right. So there, we've got that. But you know, when we're looking at some of these trees, height and then size. Standard, min. This tree was 2. The height was 6. What are we looking at here? That's gen, no. So after gen, we have max and then min. Okay, so 100 max min. So some of these trees were really small. So the blow control was doing a good job. 6 and 1. Let's change it to like D6. Run. I'm just curious how poorly this computer is chugging along. Oh, Sentinel-1, thanks. Yeah.
Secure because it's so slow.
So, see, now you're thinking. All right, so it looks like the best candidate solution on this data was x plus 5, but it had a mean squared error of 24. That's not pretty good.
16.
Try, what?
Try 16.
The number 16? Oh, try 16? Why, which one, why, what's that one?
I don't know.
You just want me to try another one?
Well, that's the one I did for my assignment. So.
Holy moly. So, not looking very good.
Yeah, I got to 0.5.
So my first thought is, maybe, so that's a small population, and that's a small. Mutation rate is, okay, I thought it was 50%, and I was like, holy moly, that's too high, but no, that's fine. Max height, that might need to change a little bit. Let's make it 7, 64. Tournament size, yeah, Typically with GP, you have hilariously large populations. 100 is not hilariously large. But because I'm aware that this computer is struggling as is, I'm not really gonna do much. So I'm letting it go for 1,000 generations, and we're only at 50. But what is it? Any vowels min, so fitness. So our fitness values are getting smaller, but the problem is we're still at like times 10 to the 8. And I'm really seeing not really any, and it seems as if there's no elitism here, which is fine. But like I'm looking at this column right here. So we're down at 5 times 10 to the 8. Clearly it's improving.
Looks like it's improving slower and slower.
Yeah, I'm worried it's going to converge a little bit. Maybe, I mean, let's just watch how this goes a little bit longer. 5.2. Is it 5.1, 5.2? See, we can see some imps. Something funny's going on there. It seems to be stuck around 5.2. Did you observe something similar when you were doing it?
To start with, it was quite bad.
So my gut is telling me, oh, whoa! Whoa, something just happened. Something crazy happened there.
I have to watch a replay of that one.
Yeah, let's go back and see what happened. I saw it, I was like, oh, there was a 7. Holy shit, wow, that's a 6. Oh my, wow! Crazy, what are we down to 5? 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2. Hey, okay. So, hey, there we go. Just simplify this.
What happened in like the third last and fourth last generations there?
The nans? Probably there was like an infinity there, or something that like the number got so big that Python was just like, we're calling it infinity. And then when you started to try to do any like averages or anything like that, it got weirded out, and it was just like, you could. I'm not sure how it would change, but there is like nan mean and nan STD, which means ignore standard deviation.
But like those are best values. Like was the best value name? Like did it lose every single? Like I was confused.
I'm guessing. I'm not. Blah, blah, blah. I would need to know exactly how Deep was calculating all that, and it might be done with some fancy stuff in the back end to make it quick. That maybe it did some modifying. It's hard for me to say. Clearly, the population didn't.
All died because of the
Yeah, but like, look. 1, 2, 3, 4, 5, 1.9. I mean, that's not bad, right? That's not too bad. I mean, I wonder what that looks like. Now, my gut is telling me that maybe the language needs a tweak. Okay? My gut is like, well, maybe its restriction is what I'm including in here. So first and foremost, let's get rid of the negation. A smaller language is better in that it reduces the search space size. But of course, it needs to be sufficient to be able to cover what we want to fit. So let's,
Because really negation is just 0.
yeah. So it's almost like redundant, right? So instead of protected divide, let's do, do we import math? Looks like it. And you know what? I'm not going to bother with tan. Tan's a weird one. Let's hope to God it's not in there.
You can get tan from cosine sine, so you're fine.
There we go. All right, you ready? Let's do it again. Let's see if we can get close to times 10 to the 5 quicker than, what generation was that? Around generation 700 and... Around generation, look at that, around 800, it got,
Which column is the average again?
I don't know, this one?
I just wondered if the average shot down too, or if it was just the best.
So min, max, gen, average. Okay, so 1, 2, 3, the third one over. So we went from like times 10 to the 9 down to
Alright, so the average didn't change.
the average got worse. All right, let's see what happens this time. Oh no, what did I do wrong?
I had to think off too. What's happening is sine and cos are being passed infinity, and they don't like being passed infinity.
Huh. So what did you do about it?
I wrote a protected sine and protected cosine, essentially, that just handled infinity there.
I was afraid of that. And what did you return?
Infinity.
Infinity? Yeah, all right. Let's.
Super zero, I can't remember. I think I might have tried both.
Because the range of sine and cos is either going to be like,
-1 and 0.
yeah. So I'm inclined to put in 0.
I think that's one.
Why not? Well, the the domain of it would be infinity, and then it just, you don't know if it's going to be between 0 and 1. So just like,
I think it's
Yeah.
1.
I would just say like 1/2, just guess, like, do it. Actually, no, because then you might get good fitness values for something like that.
Dying.
Pardon?
The math side of me is dying.
Or what we do is we say, all right, see you later. Now, you know what? Because I'm noticing we're running a little low on time, I want to show you something what I think is interesting. But this all depends on if I can find it. So sometimes I might have some data from a function that, here, let's go. Maybe under research projects, GP fun. All right, so this isn't the one I wanted to show you, but oh no, is my computer not plugged in? No, it is. That was apparently very difficult for this computer to do. Holy God. Sentinel-1, like, get the F out of here. I know why the computer worked a lot better on Linux. Jesus. So, here's just an example. This isn't the one I had in mind, but this will do the trick for now, just because I don't have enough time to go find, maybe I can find it after I at least try to explain this one. So the question, I was talking to, at the time they were Dean of Science at Western, and we were kind of talking like, when humans discovered a Fourier transform, when humans discovered some mathematical property, right? Like, just because, when we discover something, there might be a million other ways to discover that same phenomenon, all right? And You know what, let's not go that deep. Okay, look, here's the problem. We said, can you, GP, here is a stepwise sine wave between negative pi and pi. All right? All of the data points, let's get rid of this. So the blue is a stepwise sine wave. It's a sine wave, but it's just like if it's positive, it's 1. If it's negative, it's negative 1. Right? It just jumps between there and there, right? It's not a nice continuous sine wave. So it's a stepwise sine wave. And I only gave the GP system these data points. Between negative pi and 0, I gave it negative 1. Between 1 and between 0 and pi, I gave it 1. Right? That's it. And I told the GP system to fit this data. The GP system had no shot in hell to fit this data perfectly. It can't. It's not possible. Okay? But I gave it like sine and a bunch of other operators in the language. But I said, do your best. And so there's an interesting phenomenon. Okay, I'm trying to think how best to tell this story. It's been a while since I've told the story. When you look at this, at the end of the day, after I ran this, the orange line is what the GP system came up with. Okay? And I would say, hey, look, that's pretty interesting, right? It's trying really hard. If you zoom in, it looks like this is probably coming off the line a little bit here. And we can see, obviously, it's not perfect. But goddamn, if this is a real problem, the toy problems I gave you are, I use a mathematical function to generate this thing. Can you tell me what it is, okay? But here, imagine this is a real phenomenon and I want to fit it. And you look at that and you're like, it wasn't a perfect fit. But I respond with, I don't need a perfect fit. I need a good fit. And this is a damn good approximation. This orange function, I don't remember what it is. This orange function is a damn good approximation for a stepwise sine wave between negative pi and positive pi. In fact, what's even more interesting is it even appears to be pretty good once you get past negative pi and positive pi, too. The orange line actually fits the blue pretty well regardless. And I've got some other examples here, too. And then this one, I think this one was try to fit the sine wave without sine. Yeah. Here it is trying to fit the sine wave. Blue is the sine wave. Green are the data points that I actually gave the GP system. And orange is the function it came up with. And I said, try to fit the blue line. If I said, here, in the language you have sine, yeah, it'll figure it out, right? But I didn't give it sine. I didn't give it like any trig operators. Maybe, no, I don't remember what I gave it. But that's actually not that bad of an approximation of a sine wave, despite not having the sine operator. And what was interesting here is, there's this idea that you can actually, any periodic function, you can break down any periodic function, no matter what you look at. You give me any signal, all right? Any signal. And it's possible to break that signal down into a sum of scaled sine waves. It's a linear combination of sine waves, any signal. All right? Raise your hand if you were aware of that before. Yeah, okay. Do you remember what you call that thing? Yeah, sure. So, but when my GP system was doing, meaning you could basically just create, it's possible to create a scaled sum of sine waves that does the stepwise, right? But the GP system, it's not going to be like infinite long. There's a limit on how deep those trees can be and whatnot, right? But what was interesting is this approximation wasn't doing a sum of them. It was nesting the sine waves inside each other. So that then begged the question, like, okay, obviously there's multiple ways you can approximate this thing, right? And just because we invented it, we thought of doing it one way, doesn't mean it's not possible to do a similar thing another way. And then the question was like, I remember they posed it was like, how do aliens do like fast Fourier transform or something, right? Where it was, like, you know, if civilization were to end today and a couple of people survive, a couple of people that currently live in a cave and they retake over the world and they rediscover things that we've discovered, a lot of it they're going to discover the same way. But there might be some interesting things that they discover. They might discover some of the same things we discover through a very different means of making that discovery. Long story short, what's interesting about GP is GP, genetic programming, isn't biased by preconceived notions that we have. It's not intrinsically biased by some of the preconceived notions of how we go about solving some problems, meaning it can come up with some really creative solutions that we'd never think of, which is pretty cool. Anyways, that's that for now.